Chemical reactions in Unit 7. What we're going to be looking at in this unit is chemical reactions, the specific types of chemical reactions, and why do they occur. So what I want you to think about to yourself is, what is a chemical reaction? Why do chemical reactions actually take place? This is something we've actually talked about in previous units. I want you to start thinking about the valence shell, valence electrons, and the octet rule. So, chemical reactions. What is a chemical reaction? Well, a chemical reaction is a rearrangement of atoms creating a new substance. When you start with something and you end with something different, you know a chemical reaction has taken place. You're changing the chemical composition of what you started with, your reactants, and changing them into something different, which is your products. In my example down below here, you can see that propane and oxygen react together to create carbon dioxide, water, and some type of heat and light. An example of a chemical reaction. Another way a chemical reaction is taking place is it's indicated by a color change. Bubbles, such as a gas being produced, or precipitate. Precipitate is a solid. So sometimes you'll see this as abbreviated as PPT, meaning precipitate. So you can look at the following examples, and you can see that I had a yellow solution and a white solution causing a yellow and red solution. So I know a chemical reaction took place. The next thing here we have is some precipitates. Okay, this one actually looks like there's some bubbles forming right here at this portion here. Okay, and some foam developed. So we know we have some type of gas being emitted. So we didn't start with a gas, now we're ending with a gas. And then the last one, I have a precipitate, so a solid. I started with liquids, now all of a sudden I have a precipitate or a solid. And you can see that this murky color here is indeed your solid. Last part about a chemical reaction is that they're made up of reactants. They change into products. And these products have different properties. Going back to my initial example with the propane and carbon dioxide. Propane, you can cook your dinner with. Carbon dioxide, you're not going to be cooking any dinner with. So overall, chemical reactions we know take place based off from three things. We have a rearrangement of atoms creating a new substance altogether. We can physically see this change based off from color change, the production of gases or bubbles, and the production of a possible precipitate or a solid. You don't have to have all three, just one of the three. Then the last one we have there is made up of reactants that change into a product, and then we know that these products are going to have different properties because they're completely constructed in a completely different manner. So when we're looking at paper, we look at chemical reactions in a couple different ways. What I want you to do is I want you to try to write the word equation, or now the chemical equation for the word equation below. So we're looking at zinc, lead 2 nitrate, yields or produces zinc nitrate and lead. As you can see, based off from the word equation, my lead is with my nitrate, but on my product side, now the zinc is. We're going to talk about this specific type of reaction, but I want you to take a second and I want you to try to give the chemical equation. So going back a couple units and going from the word to the chemical symbol. So looking at zinc, we know zinc is Zn. Lead 2, remember that 2 tells us the charge of our cation, which is our lead. And we can determine the charge of our nitrate ion by looking at table E. Then we have our production of our zinc nitrate and our lead. Based off from the correct word equation above, we should end up with the following chemical equation. So we're starting with zinc. Zinc has no net charge. We're starting with lead, which has a 2+ charge, and we have our nitrate, which is a -1 charge here. So +2, -1 times 2 gives you canceling charges, so this all is neutral. And then the zinc actually ends up replacing the lead here. Lead we know has a 2+ charge. Again, the nitrate with a negative, so we have to have 2 of them. And now our lead, which actually has a overall 0 charge. Remember, anything on its lonesome has an overall charge of 0. Looking at the next one, I'm telling you that I have 4 aluminum, so I have a coefficient out in front. And I have 3 oxygens, another coefficient. Produces or yields, in this case, 2 aluminum oxide. So thinking about our naming system, we have aluminum oxide. And based off from that, we should be able to figure out the chemical equation. Well, first off, if aluminum's by itself, what's the overall charge? Oxygen is one of those special 7. So oxygen, remember, doesn't appear by itself. And then we have our aluminum oxide. So I'll give you a second to write that down. And based off from there, if we have 4 aluminums, I use my coefficient telling me I have 4 aluminums here, all in the solid state. I have 3 oxygens, remember O2 because it's a diatomic molecule in the gaseous phase. And when these two interact, you actually produce 2 aluminum oxides. Again, looking at this, we know the charge of the aluminum is a positive 3, and we know the charge on the oxygen is a negative 2. Using our crisscross method, our charge of our cat becomes the quantity of the anion, and we know that the charge of the anion becomes the quantity of the cation. And then we have 2 of those. We're going to talk about the use of coefficients in just a minute. So why do we use coefficients? Well, it goes back to the idea of conservation of matter we talked about on the first day of school. Conservation of matter is that we know that mass is never created nor destroyed. So all balanced chemical equations show conservation of mass by using coefficients, those numbers out in front, which we just looked at. For mass to remain constant before and after a chemical reaction, we have to have the same number of atoms before and after the chemical reaction. So each element must be the same before and after a chemical reaction. If you look at my little graphic here, you can see that the gentleman started with 70 kilograms, put the 2 things together, they ended up blowing up, but he still ended up with 70 kilograms. Again, showing the conservation of matter. So counting atoms in a reaction. How do we count atoms? Well, to count atoms, all you're going to do here is you're going to look at the leading coefficient and multiply it by any subscripts that are associated with the atom. Remember that a subscript shows the quantity of the atom present or before it. So in this case, how many hydrogens do I have? Well, I have a subscript of 2, so I know I have 2 hydrogens for every 1 oxygen. Well, if I'm looking at a multiple or a coefficient here of 5, 5 times 2 should give us a quantity of 10 hydrogens. Well, 5 times 1 would give us a quantity of 5 oxygens. So looking at those, you're going to remember to use the quantity or the subscript of the individual atoms and then multiply that by the coefficient out in front. So if you're looking at iron, iron has 2 for every 3 oxygens, but a coefficient of 2. 2 times 2 will give us 4. 3 times 2 will give us 6. Looking at our next example here, we have 2 of all of this. 3 sodiums for every 1 phosphorus for every 4 oxygens. Well, if I have 2 of those, I'm going to have 2 times 3, which is 6. 1 times 2, which is 2. And 4 times 2, which is 8. In our last example here, I have my aluminum, I have 2 of those. And then I have my sulfate, which I actually have 3 of those. So this one gets a little bit more tricky. So when you have a subscript within a subscript, you have to multiply them. So let's start with the easy one. Aluminum is 2, and I have 3 of them. So 3 times 2 would give me 6. Sulfur, I have 3 of the sulfurs, times 3 will give me 9. Now I have 3 times 4 times 3, which gives me 36. Again, by showing and using coefficients in our subscripts, we are showing the conservation of mass. All balanced chemical reactions actually show the conservation of mass, energy, and charge by the use of coefficients in front of each molecular formula, as we just saw. For mass to remain constant before and after a chemical reaction, remember the number of atoms of each element must be the same before and after a chemical reaction. These 2 statements demonstrate the law of conservation of matter. So please join me in the next video as we're going to balance some chemical equations.